Today we're going to talk about hypothesis testing for two independent samples, and we're looking at calculating the mean. And we're using our usual 6-step process to do this. So when I say independent samples, we want to make sure we understand what I'm talking about. Independent samples are not related to each other in any way, as opposed to dependent samples, where there is a direct correspondence from elements in the first sample and elements in the second sample. This is sometimes called paired or matched samples. The formulas are a lot different for this, and it's usually where I'm doing something like maybe a before and after with the same group of people. And so it's technically two samples, but I'm comparing each person to themselves after doing some kind of treatment on them. In independent samples, I have double the data that I would normally have in a one sample hypothesis test. So 2 population means, 2 population standard deviations, and 2 of everything for the sample as well. So a lot of information gets thrown at you in these problems. You want to make sure you keep it all organized and labeled correctly. Because I'm looking at means where we have no population standard deviation, I'm only going to have a sample standard deviation. This is going to be a two sample t-test, and the requirements for that test is random and independent samples. The population needs to be normally distributed, or your sample sizes need to be at least 30 in order to use the central limit theorem. And our hypothesis statements look something like one of these two. So on the left, I've got where the two samples are either equal or one is greater than the other. If I subtract the mu2 over to the left side of those equations and inequalities, I get hypothesis statements that look like the ones on the right here. Sometimes it's advantageous to use the ones on the right where I'm looking at the difference between them is 0, or maybe it's some other value depending on the problem. But for this one, we're probably going to stick with the one on the left. It tends to be a little simpler if it's not necessary to write it as a difference. The difference is helpful to remember because we're always assuming that the null hypothesis is true. So if I take the difference between the mu's, I will get 0, which helps us out in the formulas we're going to look at. Now these formulas can be a little overwhelming, to say the least. If you're using a graphing calculator to do this, you're not really going to need to use any of these formulas, which is awesome. This is one of those times where a calculator has an Excel beat, because Excel does not do this stuff automatically unless you have data sets to draw on to do the calculations. Right? So we're looking at how do I do this in a graphing calculator or in Excel if all I have are the statistics and not the actual data sets themselves. So here's my formula for a t-score. Again, if the null says that the difference is equal to 0, then this piece just disappears, and it's really just the difference of the sample means over the standard deviation. The standard deviation is calculated differently depending on the variances. If the variances in your two samples are equal, then we're going to be pooling the data or combining it. And this is the formula for my standard deviation, where this sigma hat is this nasty little square root there. Degrees of freedom, if the variances are equal, is a pretty simple formula, just adding the sample sizes and subtracting 2. More commonly, though, the variances are not going to be equal, or you're just not going to know. And so in that case, we're going to use this formula for our standard deviation, a little bit simpler than the other, and then this monstrous thing for degrees of freedom. Again, if you're using graphing calculator, don't need these formulas. You only need them if you're going to be doing this in Excel. So let's look at an example. So the Municipal Transit Authority wants to know if on weekdays more passengers ride the northbound blue train towards the city center than departs at 8:15, or the one that departs at 8:30. The following sample statistics are assembled by the Transit Authority. Test at the 5% level of significance whether the data provide sufficient evidence to conclude that more passengers ride the 8:30 a.m. train. So I've got a nice organized table here. Not always going to be the case with all the data. I'm still going to take the time to identify what my N1 and N2s are and so on. So the 8:30 train is my second sample, N2, X bar 2, and so on. And 8:15 is going to be my first sample. And I've got a level significance of 0.05. Now for the alternative and null hypothesis statements, I'm going to look back at that last sentence. It says that more passengers ride the 8:30 train, so that means my mu1, the 8:15 train, is going to be less than mu2. And so that ends up being my alternative, and the null is always going to be the equality. So my claim is the alternative statement there. In step 3, we want to make sure that the requirements of the test are met, and we want to identify the tests. So this is a 2-sample t-test for a mean, and it didn't say anything about the populations being normally distributed, but my samples are both at least 30, so that meets the requirements for this test. In step 4, this is when I start getting into the calculating. This is what my t-score formula looks like here because they didn't tell me the variances were equal, so I'm going to assume they're not. And I'm going to use this formula. In my calculator, I'm going to go to my list of tests and use the 2-sample t-test for stats. Excel's going to be a little bit more work, so we'll do that one second. So let's flip over to the calculator. If I click on stat, if I had a set of data, I could enter it under the list and then go to the tests. I wasn't given any, so I'm just going to go straight over to tests. I'm looking for the 2-sample t-test, number 4. And again, if I had entered data sets in my list, I would choose data, but all I have is the statistics about the data. So I'm going to stick with stats here. All my information, I've already plugged it into the calculator. My alternative hypothesis is that mu1 is less than mu2, so I leave that highlighted. And I am not pooling the data since the variances are not equal. And then I'm just going to calculate. So this gives me a nice summary of all the things that I entered into the calculator, and it also gives me the t-score that I needed and the p-value. So very quickly, I've got everything I need to go right to that last step of determining whether I'm going to reject the null hypothesis and what I do about the claim. In Excel, it's going to be a little bit much more work. I'm going to actually have to plug in all those values to the formula for the t-score. So here I've done a lot of prep work in advance. All my data is entered here. I have this monstrosity of a degrees of freedom formula pre-programmed in. And the nice thing about setting this up is now for the next problem, I can just change the data and it will recalculate. So if I start changing things, it will recalculate that degrees of freedom. You can see this matches the one I got in the calculator, so I'm feeling good about this. And I'm going to go straight to the t-score formula. So I need parentheses around the subtraction. u1 minus mu2, x bar, divided by square root. And there's my variance divided by n1 plus variance for the second one divided by n2. Close off those parentheses, and I get the same t-score as before on the calculator. Sorry, I got that weird error, but I am not starting over. So we're going to keep going with this video. So I got a t-score of negative 3.283 about. So that puts us on my curve right here, right about there. And mu1 was less than mu2, so this is a left tail p-value that I'm looking for. So I want that area to the left of this. On my graphing calculator, I've already got it. On Excel, I'm going to have to do some more work. I'm going to use the t.dist, plugging in that t-score and the degrees of freedom, and then go true for this one. So equals t.dist, grab the t-score, grab the degrees of freedom, and go true. If this had been right-tailed, I would do 1 minus that value to get the p-value. If it was two-tailed, I would have done 2 times that p-value there to get the final answer. So I've got my p-value. In step 5, I'm going to compare that to alpha. So it's definitely less than 0.05. And now I can go straight to that final step where I decide what to do with the null and the claim. So when p-value is less than alpha, like in here, I reject h-naught. And then I remember, okay, the alternative hypothesis was my claim. So I'm going to come over here to where the claim is HA. There is enough evidence to support the claim. So my final statement is just going to add some context to that. So there is enough evidence to support the claim that more people ride the 8:30 a.m. train than the 8:15 a.m. train. And I have finished this problem.